Good morning. Hello, everybody. Welcome to this Mind Tech Talk devoted to what we have learned during the conference Kernel Recipes 2024. My name is Olivier Lheureux. I am Senior Mind Consultant, and I am with Charles-Antoine Couret, also Senior Mind Consultant. We have both attended Kernel Recipes end of September this year.
So this event took place in Paris just after the Olympic Games, so with nice mascots. In fact, this event it's a bit cozy with few attendees, about 100 people, and only one big room to make all talks. So there is no agenda issue. The lunch is very well organized. We are able to discuss with the different speakers, which were in these pictures here. And so we have the possibility to talk to each other, which is pretty nice to discover what is happening for other people, what are their hot topics, and what they want to do, etc.
By the way, if you want to have more information about the conference, looking at the slides, looking at pictures, looking at the names of the speakers, etc., everything is on the kernelrecipes.org site, which URL is on the slide here. We will not try during this Mind Talk to give you really an understanding of the technical content. It's simply impossible to summarize in 1 hour 3 days of very high level technical content by very high profile speakers. What we try to do now is to give you an idea of the subject, let you understand what it was, and especially for me, trying to give you what personal lessons I have learned by attending that conference. My personal focus, like many mind consultants, is on embedded software, and we are also in the European Union, and we are a small business, quite often busy with small business, also with bigger businesses. There are 4 main subjects of that conference, even if it was not very explicit. The first is security with CVEs. We'll come later with the summary of one conference about it. Rust, which is coming to the kernel, especially for security, but also for reliability of the new language. Performance, about scheduling and parallelism. We will have the summary of a talk about that, but there were other talks about semaphores, scheduling of virtual machines, etc. And the last subject was real time, and especially focusing on the preempt RT patch that was just upstreamed at that time. What we learned is also the meta information, what is not really in the talks, and that is known by the coffee breaks, by meeting the speakers, etc. We could have a grasp of who are the main developers, what do they think, what are their challenges, how do they work, what kind of tools are they using, how are they financed, by the way. Also, who are the other actors than the main developers or speakers? Which people are there? Which companies are busy with the kernel? Who are the competitors for us? And also, there are possibilities to collaborate. Last year at Embedded Recipes, a slightly different conference, they invented the word co-opetition, which is the merging of competition and cooperation, because we are competitors, but we are also working on the same open software. Summary of the first conference. Title was CVEs Are Alive, But Don't Panic by Greg Crowe-Hartman. Those who do not know Greg, he is really a very high profile. His employer is the Linux Foundation, and he's, between other things, responsible of long-term releases and security of the kernel. CVEs, that's common vulnerabilities. That's the normal identification of a security problem in the kernel. And he says they used to mean nothing for Linux. They were made externally by people that do not really understand the kernel. The kernel.org community is now a CNA. That means that it's the kernel community that creates the identification, that creates the CVEs for the kernel. And they have decided to make a lot of them. So that made a lot of people afraid that zillions of CVEs would overflow their security process. Greg explained what is a kernel vulnerability, coming into the details, what it is not. And he described the CVE attribution and creation process, the review, the delays. By the way, it's about 2 weeks before they try to speak about it. They have, of course, they do everything by email. Greg said there are about 55 CVEs per week, and they do have developed tools to handle all of them, to know if some kernel, for instance, at a certain point is vulnerable or not. The CVEs are descriptive. That means there is enough information in the CVE to see if a certain file in the kernel or a certain version of the kernel is affected or not. Most of them are not for you because you don't use it. Typical example, there is a CVE in a kernel driver that do not use. It's not a vulnerability for you. You only, the user of the kernel, know if the CVE affects you or not. Greg insisted ignoring CVEs is a security problem, and cybersecurity is a hot topic, not only for the kernel, but also for the kernel. So the choices following him are either use the latest kernel or a long-term support kernel, or do the job that they do yourself, sort out 55 CVEs per week and patch your kernel 55 times a week, which is an enormous job. And the last of his message very clearly is that enterprise distros do have a problem because they try to sort the CVEs themselves and they could not follow really. What we have learned, first, we must take security seriously. We knew that already. Secondly, that the kernel community is really busy with cybersecurity. That's good news. The third point is trust them. That's what Greg asked. If you don't trust them, who else will you trust, and how could you be secure? You trust them for the code, trust them for the security, and don't try to do it yourself by cherry picking. You will never reach a decent level of security.
So the next presentation is about interfacing kernel C APIs from Rust, because Rust is becoming a topic for the kernel by making some experiences around it. So there are some talks about it. So I've chosen this one because it's more relevant, I guess, for us and more descriptive. So In fact, why they want to use Rust in the kernel? In fact, for a big project like the kernel, almost half and more of security issues are coming from memory issues. And in addition to these security issues, memory issues are introducing also regular bugs like data corruption or race conditions. So um, the issue is coming from the C language, which is used in the kernel, which is not safe, and it's difficult to mitigate them by just some policy about the code, etc., and reviewing the design. It's really difficult to be consistent and to be safe about it. So that's why I want to use Rust to be a solution for this kind of issues, because the compiler can check a lot of things to avoid these memory issues. So at this moment, Rust is only used for leaf code in the kernel, so like the driver. So at this moment, there is no plan to introduce it for a big subsystem like memory management, scheduler, or file system, etc. It's just for something like the drivers, which can be easily removed if we want in the future. But to do it, there are two possibilities, in fact. We can reuse raw C code as much as possible for the interfacing, for to call other functions, etc. But in fact, it's introducing a lot of unsafe sections in the Rust code. So we are not taking a lot of benefits in using it, and but it's quicker, in fact, to do it that way. Or we can write the code in canonical Rust code. So it means we have to make more interfacing between the C code and Rust code, which is longer, more complicated, but at least the result would be more interesting for the kernel. So he wanted to describe an interface by implementing the block message queue as a dummy driver to compare to the C implementation. And after making the implementation, it compares the performances to be sure that there is no regression about it. So the override is not quite big. In fact, it's less than 2%. Sometimes it can be faster. Sometimes it's a bit slower, depends on the benchmark, but at least it's not a big deal there. And it can be improved because some checks can be eventually enabled only for debug build and not for release build to win some time at runtime because we are sure about the behavior during the debug build, so we can remove them eventually. Also, rewriting everything in Rust can improve the API design by making it easier to use by the user of this interface. For example, to release the different resources related to a specific driver, you can provide the warranty that, okay, this release process is executed only once, and there is no risk to call it several times, in fact. So you can improve the reliability and the security of the code. But to be able to do that, a lot of things should be done at Rust level. For example, C doesn't have the data ownership representation. In Rust, you have also to initialize all structures which are used by Rust code, which is not always done by drivers in the kernel. So there are some helpers which are developed to try to solve it in a generic way, but it's still in progress and is still requiring a lot of work at this moment to be able to do that. But we can see here that, okay, it's becoming a real thing in the kernel. They are progressing, trying to make some experiences, and the benefit seems to be really nice. So we are pretty sure in the future that will be affect more code, and maybe we should have to deal with it and to learn the rest ourselves.
Next conference was by Vlastimil Babka, and he was speaking about memory. All your memory are belonging to whom? That was the title. And actually, it tries to answer the question, where is my memory? At some point, especially with embedded systems, by the way, you have a memory problem. You had enough memory, and then developing, using a new kernel, whatever, you have a lack of memory. And you want to know where did it go? Which application or feature uses what memory? And that's a problem, that's non-trivial question. Because you have virtual memory shared between the libraries, between the process. You have tools. And one of the big questions is how to interpret the data that we get from the tools and from the observability of the kernel. I take here the very simple example. The conference started by simple examples and went to more complicated. It's probably known, if you want to use free, you will see different things, but it's difficult to correlate the numbers that you see. Here you see that you have total memory, used memory, free memory, and that is not the whole. Total is not used plus free. What happens? Well, you have also the shared, the buffering, the available, etc. How do you know what it means exactly? Vlastimil actually has looked at the proc mem info. It's a file in Linux, and it allows to understand everything if you do really understand the meaning of the numbers. If you look at it, you will see that the unused memory in the Linux memory management almost does not exist, because unused memory is wasted memory. So for instance, Linux will cache all files that were ever read in the hope to reuse the cache. So you see that actually the total is the sum of used plus available and not free. What is free then? Is it available? Is it shared? And the conference explained it beautifully. I will not do it here. It's not possible. And the next step was indeed to analyze the output of proc mem info. We see here the very beginning of it. Sorry if it's small. There are 4 slides of it. Should I have not copied them all, it would take too much time. You just see at the beginning the memory total free and available there, but you have a lot of them. You see swap, active, inactive, dirty, write back, reclaim, kernel stack, page tables, commit limits, slab, etc., vmalloc total. I don't speak about the mmap things. I should have used 4 slides just for mem info. And actually, Vlastimil explained during almost 1 hour a lot of it, how to understand it, what is the data, how the memory data interact with themselves, what is used by the kernel, by user space, what is not used, and the concept like anonymous memory, page cache, mapped and unmapped, active and inactive memory. And at last, he made the same for the output of PS. So what was explained was how to debug the missing kernel memory. If you think some memory is missing, you don't know where it went, this talk will help you a lot. He also explained that a sudden non-zero swap usage is not a bug. Sometimes you get swapped in your kernel, you put the question why. Okay, that makes sense. And the lesson I have learned especially for embedded, that computer memory management is really complex. And the question, where is my memory, could be really a long journey, beware. So if you need it, learn it.
So the next talk is about a debugging tools, which is Red Snoop, which was developed to, in fact, understanding where is coming specific error in the kernel, which is a very nice tool. So it was an introduction about it. So in fact, for some subsystem like BPF, you can have a lot of errors. Like for example, here, 1,000 invalid value errors, which is quite a lot. And when you want to debug to understand, okay, I have an issue where it's coming from, can be difficult to identify the root cause. So that's the purpose of this tool, which is based on BPF and which is acting as a superset of fstress to be able to capture by default functions which are returning errors. So it means null value for pointers or with the enumeration error values from defined by the kernel. But you can also define it to capture function arguments or other return values if you want to understand, for example, what is happening, what is the scope or the environment which is triggering the error. So here you have an example of command line to set it up. So on the left, you have a call graph of different functions. When the background is gray, there is nothing which is returned. When the background is red, it's an error. When it's not really relevant, in fact. When it's green, it's a normal value, so no error. So here in the command line, you can see is adding the function e as an entry point. So it means when this function is called in the kernel, it will start the debugging session, and so to record what is happening. And it's adding also function a and b in the as a function to log. But this function will be recorded only in the function e scope. So it means function A or B are returning an error outside the function e scope is not recorded at all. This is interesting for helpers functions, which can be used by a lot of different subsystems to avoid to have a lot of noise, in fact, in your debug. So you have the translation on the right after executing the command, what is processed by the tool. So the first function A is discarded because it's called outside the function E scope. The first function A is not recorded because it's not returning an error, so we don't care in that case. But function B is recorded because it's calling function A again, which has an error. So the purpose is to have the complete trace of this code chain with relevant information. But you can customize a lot, in fact, if you want to have more details for your specific purpose. Here you have an example, so with a cat trace mode enabled. So the purpose is to see all BPF functions which are called after loading a BPF program. So you can see on the left the name of the functions and their relationship. You have in the middle the result for each function, so which value is returned by this function, and the direction to execute each function on the right. So you can have all logs here. The idea is just to see, okay, OBPF is handling a BPF program in his example. There is another possibility to see is in the stack mode. So on the left, you have the duration to execute functions and the return values for each function. In the middle, you have the stack of function calls. And on the right, the different files with the line to identify, okay, where the function is defined. In fact, if you want to see the code itself to understand what is happening. You have a lot of more possibilities to identify also, okay, this function is called, but with which arguments, etc. There are some helpers for that. So it's, in fact, a very interesting tool to be able to understand what is happening in the kernel if you have a specific issue, which looks easy to use in production. It's also already available in some distribution if you want to test it. So from our point of view, it's interesting to have it if we have an issue in the future.
Next talk was from Mathieu Desnoyers, hazard pointer with reference counter. That was a tough one. Why this talk? Why I've chosen this talk? It's an example of performance optimization. They were a good part of the talks that were about performance optimization, trying to get the same kernels and the same load running 1%, 2% faster. You can imagine that for the cloud, it's very important. There were other talks about optimization, like about semaphores and about scheduling, especially VM scheduling. I have chosen to show this one. And of course, in embedded, usually we do not touch that code because usually we are not forced to go for optimization at that level, but we benefit from it because we reuse the same code. And especially about speed, it's very important for real time, and real time is important in embedded, and also using less memory is very important for embedded. What are hazard pointers? It's a variant of RCU. And I don't know if you know RCU. It's read, copy, update. It is a mechanism for thread synchronization when accessing some data structures, typically linked lists, sometimes trees, and other data structures usually linked by pointers. And the very interesting property there is that there is no lock. You could say, is it magic? It never blocks, and you do synchronize the threads. So it is very much optimized for read performance. But RCUs have a disadvantage. It uses possibly, usually with the kernel, a lot of memory. And it's used in the kernel for memory management and also for the networking stack. The difference between hazard pointers versus RCU is that with hazard pointers, you have a faster memory reclaim. So you use effectively less memory, and for embedded, it's important. And the challenge is always for all those methods to guarantee the existence of objects so that you are able to dereference a pointer without crashing. What does Mathieu do? He implements reference counters with hazard pointer. I think everybody knows reference counter. I will not explain. He has an implementation. He has before an implementation in user mode that he ported to the kernel. And he made then some benchmarks of the use of hazard pointers for implementing the reference counter. at least a part of the reference counter so that the reference counter read part is made faster. There is a fallback that is normal reference counters. And he obtained that he can do it 2 times faster than RCUs. That means that during a certain time with a certain load, he could do 2 times more operation with header pointer than RCUs.
Can you explain what a header pointer is? Because that's no.
I can try to explain. Question of Arnaud here. Can we explain what header pointers are? We can try, but it would really take too much time, and we cannot afford that time here. It could be the subject of a next MindTech talk by Arnaud.
So the next talk is about virtme next generation, which is in fact a tool to more to test the kernel. So the context is about the testing of the kernel itself, which is a pretty difficult task, which is a slow process, especially if you are using a specific configuration with specific hardware or real file system to be able to identify some bugs. And depends where you are debugging in the kernel. Sometimes some tools are missing also, so it's not either to use it on real hardware, but it can be needed. And doing it can be also risky, in fact, because if you want to test it on your real hardware or real file system, if you have an issue, you can break your computer, corrupt your file system, which is not an ideal situation, of course. So, in fact, this tool is deriving from virtme, but to be faster than this one. The purpose is really, okay, we are building the kernel based on the specific configuration, and then we run it against minimal rootfs to be really fast in this process. It's just a kind of Python script, which is a wrapper of QEMU and KVM, so it's not the purpose to replace Docker or libvirt, for example, for virtualization or containers. It's really dedicated to test the kernel. So in terms of speed, starting the system after some optimization is just 1 second, which is pretty fast and allows you to use it in the continuous integration system, in fact. And it was not expected, but some projects are already using it for continuous integration, like Meter or Scheduler external projects. It was unexpected, but in fact, due to the purpose of this tool, it's pretty relevant because it's easy to dissect or to test a software to a specific version of the kernel and to execute some tests really quickly. So here we have an example to build and to run a kernel based on the modules loaded by the host. So as you can see, the build is taking only 85 seconds, and then it can run its system with the new kernel, and it can have a shell to execute any relevant test or to debug internally what is happening. But it's also using this tool for its kernel workflow. Here is showing an example that is downloading a patch from the Linux kernel mailing list, applying this patch set, building the kernel against this new source code, and run the new kernel, in fact, to be able to run again new tests if we want. So it's really interesting to show a real case example which can improve the productivity of the developer himself.
Working toward upstream first by Kernel Orazgalieva. She is from Amazon Web Service, a well-known main cloud provider. And we could there grasp a look at the problems they have there. So Amazon Web Services use the Nitro, don't know the pronunciation, hypervisor. And the target of this hypervisor is to say secure first, compliant, to offer the new features by upgrading the Linux. It's based on Linux. It should be fast and have no regression. That's their target at AWS. So they need to float as much as possible, to upgrade with the Linux kernel development, which is always a challenge because the development of Linux is very fast. They need to pick up stable updates and stay close to upstream. Upstream means the Linux kernel latest version. They used to have about 1,000 Git patches on top of Linux to be rebased on long-term support releases, to be reviewed, tested, deployed. And that's a lot of work. It's work for certainly a team of 3 persons continuously. And today their observation is that rebasing the kernel, their patches, is hard, slow, and error-prone. They have tried to manage it, and their solution is to upstream their patch as much as possible. And if they can't, to try to drop the patches. They could do it partly, starting from more than 1,000 patches. This year they were busy at the time in September with about 950 patches. Next year, they have very good opportunities to go to have that 425 patches. That will make their kernel maintenance process sustainable.
So this talk is about the current RT patch. In fact, these 2 conferences have a bit of overlap, so that's why I'm presenting them together, because I guess it's not relevant to just take one of them. We can merge them together. So the context is this real-time patch, in fact, was recently merged in the mainline kernel, which is a very good step because it was a very big out-of-suite patch for more than 20 years. But in the meantime, a lot of features added in the kernel came from this real-time patch. And that's the interest of these talks, to review, okay, which features are coming from this big patch. And it means also over the time, Linux was becoming more and more real-time capable. So even without having strong real-time requirements, you were about to use in some real-time context without any problems, and also for your desktop or server, some improvements are coming from that. So that was also the interest to progressively moving some features from real-time patch to mainline. But even if the real-time patch is now mainline, some parts are still out of suite, especially for ARM 32 bits and PowerPC architectures, because some works are still required. But it's already a big step which was done recently. So the list of features is just sampled, not all of them are there, of course. The first thing is the mutex lock and unlock mechanism, because before that, in fact, they are using semaphores for this stack, which is more complicated. for just a mutual exclusion mechanism, and the API is also easier to use in that case, and it's an improvement provided by the real-time patch. Also, the policy to remove the regular tick in the kernel and the high resolution timers are coming from there too. Why? Because the regular tick in the kernel can introduce, in fact, latency to execute some code or processes, and high resolution timers to improve also the latency after making a sleep, for example, or to execute some interrupts. So that's why it was developed first for real time. The locked mechanism also was developed in this context to avoid a deadlock when you have a chain of lock, to avoid the situation that you have a cycle in this chain of locks, to identify them and to mitigate them before having the deadlock issue. We have also the policy for the piece thread to inherit the priority from the main process to avoid priority inversion, which is a big issue in real-time context too. The interrupt threads were developed in this context again. I guess if you are writing some drivers in the kernel, you have already seen that. You have the bottom alpha approach, or just having a small function to record a specific event and to process it later in the seconds function. And using this mechanism allows to process it with a real-time scheduling and not introducing too much latency if some real-time processes are waiting to execute their own task, in fact. Also, the ftrace subsystem was developed in this context to be able to measure the latency in the kernel. Okay, I have an interrupt when I am executing the thread to process it, for example. So that was the purpose, which is now used everywhere, even in other contexts. And this subsystem also introduced the possibility to change the code at runtime to avoid any override when we are not using it. So it means if you are not using ftrace because you are not debugging something, you don't have the override to have it in the code somewhere, which is an important improvement. Also, printk was changed a lot and was the latest issue to merge it in the main line. Now we can call it from any context without introducing too much latency. So it means we can have the possibility to debug some things even in some interruption context or when in early boot, in fact, of the system. And to improve also the speed of the build of the kernel, they introduced a local mode config to speed it up. So it means that the modules which are loaded in your system are in fact making the configuration for the kernel to build only these modules to avoid to compile all of them, even if they are useless for you, which is really important to make some tests in the development of the kernel. And there are, of course, some other examples which are coming from there. So it was really interesting to know, okay, these features are coming from real-time patch, and it's just not about real-time capabilities. And they have shown also some examples of products developed with real-time capabilities based on Linux system. So here is a PowerRail developed with a cycle of 150 milliseconds of maximum latency, which is not very strict, in fact. But here it's it's a bit more complex to handle. It's ARM which is executing some function in a factory. And here the maximum latency is about 4 milliseconds, which is not simple to develop. And also to process some audio. As you should know, audio processing require to have a low latency to avoid disruption in the audio rendered by the device. And there are a lot of other examples, of course, but it's just showing how Linux is versatile in this context, in fact. And the last presentation is about the scheduling, which is in fact the project scheduler external, which is a module to in fact simplify the test and the development of new scheduler for the kernel. Because the scheduler in the kernel is a very core part, but which is complex, in fact, to test and to develop, because we have to handle a lot of different situations. We have to change the code, build the kernel, then reboot the system to see, to make any measurement and to see if we have regressions or if we are improving something, etc. So it's a complex task at this moment. So, and also, he mentioned the important properties to have for the scheduler. It should be fair for all processes, so all of them should have some time to execute their own task, obviously, but also the result of the scheduling should be optimized with low overhead. So we don't want to spend too much time in the scheduler to decide which task we have to execute, but also we have to minimize the amount of time to execute all of these processes, because sometimes they have some critical sections, they are waiting for something, so we don't want to spend too much time to just, oh, wake up, I don't have something to do, okay, you can sleep a bit and we'll execute the next one. And which is really difficult also to provide, is to be really generic for all cases. In fact, Linux is executed in server context, embedded systems, desktop, and other kind of devices, and with a lot of different workloads. It's really difficult to provide a generic algorithm to handle them without and being optimal for all of them. So that's why he developed this this module to in fact providing a way to change the scheduler at runtime. It's based on BPF, so there are some nice properties. We can do, of course, runtime changes, but also we are sure it will not crash because the BPF compiler will check it. And in case of issue, in fact, there is a fallback to use a regular scheduler if needed. And because it's loading, in fact, a different program, you can develop your own scheduler to fit your needs. And it was done in production by Meta for their infrastructure, and they measure up to 10% of improvement, which is not a small thing. And it was recently added in mainline too, so you can use it if you want. So he made a demonstration of this tool. He used a nice tool, in fact, Perfecto, to be able to see the traces of the scheduling. So you can see when each process is executed, so you can measure everything and to see, okay, we have, in fact, a lot of latency between two execution of a specific process or not. And as a test, he wanted to execute a little 2D video game with, in the meantime, a stress test tool. And what we have seen is the video game was really laggy. So you have a lot of frame issues, not processing the inputs really fast, etc. Because in fact, the default scheduler is too fair. It means that it's allocating the same time for each process, and even if a process is returning earlier than expected, it's not giving more time later and sooner. So he wanted to develop another algorithm which is used now in the main scheduler in Linux to take into account that, okay, a process is finishing earlier than expected, so it's not consuming all of its time slice. So I will execute it sooner than other processes which are consuming all of their time slice. And in that case, for a specific process which is not executing a lot of functions, but which wants to have to be executed often, it's a big improvement. If our video games like this one, it can reduce the lags, and with the same demonstration, there is no lags anymore. So it was an interesting way to see, okay, how we can change the scheduling manually at runtime to test, to improve the kernel. And eventually, if you have some needs which can't be covered by the default scheduler, you can develop your own one to fit your needs. But it's also a concern because some people don't want to have a fragmentation of the ecosystem about it, because we want to have a very nice default scheduler and not having everybody having their own scheduler with their own properties and without being able to have a very nice default one. But so it's also a way to test and to improve. Yeah. So in fact, that's it. If you have some questions about any topics, any talks,
or remarks, because we are not the real speakers to answer the real questions, but we can do our best with what we have learned.
So you have 7 minutes for other pointers.
What about hallway discussions or things outside of the conferences themselves? Was there like a rumor mill or big discussions?
So personally, on my side, I have some discussion about the maintenance of open source software in embedded context also, because we want to improve the security. In Europe, we will have some constraints about it, and we have to provide the maintenance on long term for some products, and it's difficult because we are starting and the current state is not good enough. So there are some changes about it to know, okay, how are you handling this situation, etc.
But no conclusions.
No.
During we had on the Tuesday a restaurant, and I was near Mathieu Denoyer, the guy has a pointer, and he explained what machine he could use for testing. And it's impressive because he says it's an Intel machine with 2 CPUs, well, 2 chips actually, and 256 CPUs, each with 2 threads. It's horrible. It's impossible to stay in the room when it's running because it's so noisy. And so you can imagine a little bit by what he said, what is testing for him when it goes over testing thread synchronization in the kernel. It's really a torture test on the biggest machine you can imagine. That's the kind of thing you learn there that is in actually the meta information. Another...
So you say the biggest machine you can imagine. Actually, I have ex-colleagues who work on high-performance computing, and they have like 2,000, 4,000 cores in NUMA, of course. and they run Linux on that. So it's
yeah, I know you can go further, of course. There was quite a lot of people more focused on cloud machines than embedded. It was not a very much embedded oriented attendance, which does not mean it was not interesting for embedded. One other thing I've learned, yeah, I was speaking with Stephen Rosted, and he said he works, for instance, almost 100% remotely. He almost could force his employer, Google in this case, to accept that he would work remotely because those top level kernel developers, you cannot find them where you want and when you want. And so if you want them, they are able to a little bit push very hard around condition, which is nice for them.
And he started to work on F-Trace just as a few weeks project, and 20 years after, he's still working on it.
And he explained also privately that indeed the real-time patch was really a driver of many good positive changes in the kernel. That was a sort of benchmark. Hey, we want to do it, but up to now we can't do it. We do see what the kernel preempt RT patch is doing. Yeah, that's a good idea. Let's adopt it. And also the time that it's needed. Andreas Seawar was there. We couldn't talk a lot with them. He does not talk a lot. But he really shows how you need to be long-term thinking when you speak about development in Linux. 1 year, 2 years to develop a feature and to integrate it and get it upstream, it's normal. In the embedded software I know, people want to develop a new feature in 3 months. That's simply not possible. That's not the same time scale for Linux development. Other questions? I think in this case, for this time, we can stop on time. Thank you, everybody, for attending. I hope you found it interesting. For the links for the conference, you do have the kernelrecipes.org/2024 URL, where you will find the slides and also the presentations on YouTube and the pictures and everything. For this presentation, I think you can go to Mind's blog, mind.be, and you will find within some days the links and the slides we have been using now. Thank you, and see you within 2 weeks.
Yeah, thank you very much.
Right. Thank you. Bye-bye.
Bye.
Thank you. See you soon. Bye-bye.
Goodbye.
Bye.